Chapter 1.10.11 Pod Priority and Preemption. Summary. Pod priority in Kubernetes sets importance levels, allowing critical pods to be scheduled first. Preemption helps manage resources by evicting lower priority pods for pending high priority ones. Priority class objects define these priority values, mapped to names. Higher values signify greater importance. Admins can control priority class usage to avoid misuse. Preemption can evict pods for scheduling if resources are scarce, subject to pod disruption budget compliance. Priority and COs influence scheduler decisions but operate independently. Pod priority and preemption. Kubernetes version 1.14 introduced priority for pods, which helps determine the order in which they are scheduled or potentially preempt lower priority pods. In situations where resources are scarce, the scheduler might remove lower priority pods to make room for higher priority ones. There is a risk of misuse by malicious users who might set their pods to high priority, disrupting the system. Administrators can use resource quota to limit the creation of high-priority pods. How to use priority and preemption. Add one or more priority classes to use priority and preemption. Create pods with priority class name linked to the priority classes. Use deployment or similar instead of direct pod creation. Kubernetes includes system cluster critical and system node critical classes that prioritize essential scheduling. Priority class. This YAML code defines a new priority class named high priority with a value of 10000. It is not set as the global default priority class and is described as being intended for use with XYZ service pods only. A priority class is a non-namespaced object linking a priority class name to a numerical priority value. It includes fields like name for identification and value for the priority, with higher values meaning higher priority. Names must be valid DNS subdomain names and can't start with system. The value range is between -2,147,483,648 and 1 billion. Optional fields are global default, for default priority values, and description, usage guidelines. Existing pods have zero priority unless a new priority class with global default is introduced, affecting only new pods. Deleting a priority class doesn't affect existing pods using it but stops new pods from using it. Non-preempting priority class. The code defines a priority class named high priority non-preempting with a value of 10000. It sets the preemption policy to never, meaning that pods with this priority will not cause other pods to be preempted. The global default is set to false and the description specifies the behavior of this priority class. Kubernetes version 1.24 introduces a feature where pods with the preemption policy never are placed ahead of lower priority pods when scheduling. However, they cannot preempt other pods and must wait for available resources. These non-preempting pods remain in the scheduling queue until resources are free and are subject to scheduler backoff. If unscheduled, they will be retried less often, allowing other lower priority pods to be scheduled before them. A preemption policy of never helps in scenarios like prioritizing data science workloads without interrupting ongoing processes. Such high priority pods are queued to run when resources become naturally available. Pod priority. The code snippet defines a pod named Nginx with the label env test and specifies a container running the Nginx image. The pod is assigned a priority class named high priority, which indicates its importance relative to other pods for scheduling. Priority classes in Kubernetes allow for prioritizing pods based on specified classes. When creating pods, you can assign a priority class to determine their importance. Pods without a valid priority class are rejected. The admission controller ensures the priority is set in the pod's specification. A YAML example shows how to configure a pod using a priority class, where the priority resolves to 1 million. The set priority affects how and when pods are scheduled by the scheduler. When pod priorities are active, the scheduler creates an order for pending pods based on their priorities. This means higher priority pods are considered first in scheduling queues. If a high priority pod cannot be scheduled immediately, the scheduler moves on to try and schedule lower priority pods, ensuring the most efficient use of resources. Preemption. ### pod scheduling and preemption. * pod scheduling queue *. When pods are created, they enter a scheduling queue, waiting for the scheduler to place them on a suitable node. The scheduler checks nodes to ensure they fulfill the pod's requirements. Pending pod P and preemption *. If no node meets a pod's needs, preemption begins. The scheduler looks for a node where lower priority pods can be removed, allowing pod P to be scheduled. If successful, the nominated node name field indicates the reserved node for pod P. ### handling preemption. Graceful termination *. Preempted pods get a period to finish their tasks before being terminated. During this period, the scheduler may find another suitable node for pod P, altering nominated node name and node name fields. Higher priority pods *. If a new pod with a higher priority arrives while waiting, it might take the node initially reserved for pod P, causing the scheduler to look for a new node for pod P. ### pod disruption budget, PDB, *PDB limits *. PDB allows limiting simultaneous disruptions in replicated apps. The scheduler attempts to honor PDBs during preemption, but it can still disturb pods if no suitable alternatives are found. Limitations PDB compliance during preemption is best effort and not guaranteed, meaning disruptions may occur despite PDB settings. ### interpod affinity. Preemption considerations Nodes are only preempted if removing lower priority pods allows the pending pod's scheduling. Affinity rules If the pending pod has affinity with lower priority pods, they can't be eliminated, meaning preemption won't be applied, and the scheduler searches for another node. ### cross-node preemption. Preemption limitations For pod P to be scheduled on node N, a pod on another node might need removal, which current algorithms don't support. Future consideration There is potential to develop cross-node preemption in future revisions, pending performance feasibility and demand. ### key insights. Efficiency measures Reducing the graceful termination period can shrink the time gap for pending pod scheduling. This entails setting shorter termination periods for lower priority pods. Strategic affinity Setting interpod affinity toward equal or higher priority pods prevents scheduling issues from affinity rule conflicts. Troubleshooting. Pod priority and preemption can sometimes result in unwanted issues within a computing cluster. Unnecessary preemption occurs when pods with mistakenly high priorities displace other pods as resource availability diminishes. This is set through the priority class name, which if set too high, can result in unintended preemptions. To mitigate unwanted preemption, adjust the priority class name of affected pods to a lower class or leave it empty, defaulting it to 0. Preemption should only occur when a cluster lacks resources for a high-priority pending pod. If preemption occurs without a pending pod, or if the pending pod has a lower or equal priority to the preempted ones, it signals an error that needs reporting. Victim pods receive a 30-second termination period before forceful removal, making way for the preemptor. However, higher priority pods that emerge within this timeframe may take the preemptor's place, which aligns with the expected behavior. When scheduling a pending pod, the scheduler looks for nodes with the lowest priority pods for preemption. If none are feasible, nodes with higher priority victims will be considered until a suitable node is found, adhering to disruption rules. Interactions between pod priority and quality of service. Pod priority and COS class are separate features with minimal interactions. Pod priority impacts schedulers' preemption logic, selecting targets with the lowest priority. When lower priority pods removal isn't enough for preemption, higher priority ones are considered unless protected by pod disruption budget. Kubelet considers priority for node pressure eviction. COS class helps estimate eviction order. Evictions consider starved resource usage, priority, and resource usage above requests, preferring pods within usage limits over higher priority ones exceeding them. Pod priority and COS class are independent, not affecting each other's settings. The scheduler's preemption targets are chosen by priority, aiming to remove the lowest priority pods first, and less protected. Kubelet uses priority to order node pressure evictions. COS class indicates eviction likelihood by ranking resource usage against requests. Lower priority pods not exceeding requests aren't evicted, while higher priority, over request pods may. Pod priority and COS class operate independently, influencing different features. Scheduler removes the lowest priority pods unless blocked by a pod disruption budget. Kubelet considers priority during node pressure evictions, evaluating resource usage relative to requests. Pods within their resource limits stay, while higher priority pods exceeding them are prone to eviction. COS classes form a predictive framework for potential eviction order but don't act as a barrier during preemption. Priority and COS class in pods are orthogonal with no direct dependency. Scheduler's preemption relies on prioritizing low priority pods unless restricted by pod disruption budget. Kubelet's eviction process ranks based on how well pods meet resource requests. Eviction favors stability over priority when resources are tight, often removing pods that exceed their limits. The order of potential eviction reflects predicted resource constraints, driven by COS class assessment, yet applies to existing priorities.